Hello to everyone. So we are going to start with the second plenary talk of of today. And it's my pleasure to introduce Gerard Benarous from NYU. Before NYU, Gerard Benarous was professor at the University of Orsay, as well as the École Normale Supérieure and the Swiss Federal Institute of Technology in Lausanne. So he has served the community in many ways. He headed the Department of Mathematics at Orsay and the Department of Mathematics and Computer Science at the École Normale Supérieure. He also found the Mathematics Research of Institute in Lausanne, and he is actually the managing editor, together with Amir Dembo. You was? Okay. Well, of PTRF. So Professor Gerard Benarous works in many aspects of probability in many areas, as well as in many other areas of mathematics and physics. So the talk of today is a good example of this, and he will speak about the Kac-Rice formula in highest dimensions. Thank you so much.
Thank you so much. So I want to thank the organizer for this invitation. I would also to remind, in fact, that this talk was planned initially for the, I want to give a little nod to the session yesterday organized by Jean-Marc Azaïs and José León on Kac-Rice. So I had to change my slide because, of course, now I had to make them for an audience who maybe doesn't work every day with the Kac-Rice formula. And this session was in honor of Mario Schwebor, so I want also to dedicate this talk to the memory of Mario. And so this Kac-Rice thing has happened relatively recently, maybe a few years back for me, even though Jean-Marc Azaïs and I were students together a long, long time ago at École Normale, and he has been working on Kac-Rice for a very long time. So it's fun how we are now working on the same thing. I came to this from the point of view of physics, of the high-dimensional Hamiltonian landscapes of spin glasses, of hard problems of physics. And then at some point I realized that this could also be interesting in questions of machine learning and high-dimensional statistics. This happened precisely because it was mentioned. I was the director of the Courant Institute, and at some point I founded the Center for Data Science with a guy who was then not as famous, Yann Lequin, who since then got the Turing Prize. We worked very hard on the administration of this, and one night, both being French, drinking wine, I told him, enough of administration, tell me what you're doing. And when he explained, it looked like this was close to statistical physics. So I will try to convince you that, in fact, there are some links, and of course, I'm not the first. Many people have seen that before. So let's start with this. So the title contained topological complexity of the random landscape of statistical physics and high-dimensional statistics. So, of course, in physics, the landscapes are typically the energy landscape, the Hamiltonian landscapes. In statistics, these landscapes will be essentially log likelihood functions, loss function, risk function that you want to minimize. All right, so here, the Kac-Rice formula, as we will see, gives us a way to enter the problem of understanding the topology, the shape of the landscapes in very high dimension, right? Then there is another question. Once you've understood the topology, that the landscape is terribly complicated, for instance, because of course that's what we like, then the next question is an optimization question. How do you prove that an optimization algorithm finds the minimum? So, in the preceding talk, you heard optimization is easy. Try to convince you that no. But, of course, different context. So let's go. So we'll start with first a little bit of topology and then algebraic topology, just to make sure everybody's on the same page, but don't worry, this will be fast. So how do you talk about the topology of a smooth function? Consider a function I will call f on, say, a compact manifold to avoid trouble, n-dimensional. And for me, this n, the dimension, will become very large. Think n is 10 to the 9. All right? So the question is, how can you understand the topology of the landscape defined by this function? Right? Dimension 1 or 2, you can see it. Already a function defined in dimension 3, looking at the graph of this is difficult, because you have to see it in dimension 4. Right? But in dimension 10 to the 9, you don't see anything. So this question, in fact, goes back to the 20s and to Morse himself, and Morse theory. So I'll be very quick on that. The question asked there to describe such a landscape are, for instance, the following. You could do much more, but it's only one slide for Morse theory. So the first thing is you could look at the level set or sub-level set that you call A of u, the set of points where the function is less than u, because I'm interested in finding the minimum. If you want the maximum, you would look at super-level sets. So this is a subset on a manifold. Its topology could be very complicated. For instance, you can want to compute the Euler characteristic of this thing, right? And it will give you an indication of the topology of the level set. How complicated are they? You can also want to compute the number of critical points. So this notation I will constantly use. Where is this? Yeah. This thing is the number of critical points for the function f, reminding that we're in dimension n. K and B, this means of index k. So remember the index of a critical point. A critical point is a place where the gradient is 0, essentially. The index is the number of negative direction of the Hessian. And with the values in B, where B is a subset of the real line. So you're looking at a critical value. The function is defined. This is my manifold in 10 to the 9 dimension. This is the values of f. And so you look at a certain set of values, and you look there, how many local minima or how many saddle points of index 1 can you find? All right? That's a natural question. Of course, these two are related, if you know a little bit of algebraic topology, because, of course, the Euler characteristic is, in fact, obtainable through an alternating sum of number of critical points. All right, and then, so that's what I'm saying here. I won't go there, but Morse inequalities give you constraint on these numbers, this guy and this guy, in terms of basic topological invariance of the manifold, the Betti numbers, under the assumption that f is generic, not too terrible. So generic means here that f is a Morse function, that is, this Hessian is non-degenerate at every critical point. So if you have non-degenerate Hessians, the critical points are isolated. If you have a compact manifold, you have only a finite number of them, which means that you can compute this, because otherwise you could have an infinite number of critical points on a compact manifold, right? And this Morse inequality tell you that essentially for a given manifold, you have, is there a question? No. You have inequalities between, for every Morse function. And the way this is used normally in algebraic topology is to understand something, is to use it from choosing well, a well-chosen, a smart function to understand something about the manifold, right? So that's the way it is used normally. Here we will use, so typically you want simple Morse function, as simple as possible, allowed by the topology of the manifold. Here we will see that even on simple manifold, functions can be very complicated, and try to understand how it works. So this is the title of this slide. In fact, simple functions are not that simple. That's the curse of dimensionality, as soon as you're in large dimension. So what is the simplest function you can think of? Okay, linear, quadratic, let's forget these, they are really simple. Right? Let's say cubic, right? Degree 3 polynomial, give me that. That's simple, all right? No. So let's do that. Let's consider the simplest possible manifold. Even if you don't like manifold, I'm sure you like spheres. So let's take the sphere in dimension n, trivial topology. So the Morse inequality here tell you essentially nothing. And then assume that the function is also very simple. So let's take a polynomial of degree p, okay, and let's take it homogeneous on Rn. If it's homogeneous, you can restrict it to the sphere and you essentially understand the polynomial, right? So how topologically complex can be this function, right? So let's say now n is very large, 10 to the 9, and p is fixed. So obviously it's not very complex if p is 1 or p is 2, right? If you take a linear p equal 1, you take a linear function on the sphere, how many critical points? Obviously 2, a minimum and a maximum, and that's it. If you take a quadratic form, so if p is 2, if it's take a quadratic function, a generic quadratic function in dimension n has 2n critical points on the sphere. 2 per eigenvector, right? So take an eigenvector, e and minus e are critical points. So you have 2 minima, 2 maxima, and 2 for any index you want in between. So 2n is still not very complex. But in fact, as soon as p is larger than 3, all hell breaks loose. Cubic are terrible functions. right? Here is a result which has nothing to do with probability or statistics, it's algebraic topology. In fact, the maximum finite number of critical points for a homogeneous polynomial in degree p is this. So you see, of course, that when p is 1, this gives you 2. When p is 2, this gives you 2n, as I just said. But if p is 3, this grows like 2 to the n, right? So it's exponentially large, right? So, but this is the maximum. In fact, there exists such a worst-case polynomial. To my surprise, I thought this was well known. The reference I found is recent. So you can find such a worst-case polynomial. There exists a polynomial of degree p, let's say 3, which are exponentially complex. Exponentially 2 to the n type, roughly 2 to the n critical points, right? So if you try to minimize this, a polynomial of degree 3 in dimension n, good luck, right? So this is, for instance, what came out of this discussion with Jan, and then he didn't believe me, and the Facebook team he led used as much as they had in terms of power and smarts, and of course, couldn't find the minimum. And we know, because we know what the minimum is for other reasons you'll see soon. All right, but this, this is only a worst-case scenario. That's, typical computer science type things, or algebraic topology type thing. Who cares, really, right? So let's take a generic polynomial. Take it random, right? So you take a polynomial of degree p, the simplest possible function of all, and you take simply the coefficient, let's say, to be Gaussian, IID, right? Very, very simple, random polynomial. Then this one should not be very complex. Wrong, it's also exponentially complex. Right? So a generic polynomial, a random polynomial of degree p, is exponentially complex. In fact, if you compute the complexity, it's half of the worst case. Instead of growing like n, like 2 to the n, let's say for p equals 3, it grows like square root of 2 to the n. But it's still exponentially complex. And so how do we know? This is where we come to Kac-Rice. 2 ingredients, the Kac-Rice formula, which I will detail if you don't know what it is already, and random matrix theory. So at this point, except if you've heard this talk, or read these papers, it's not clear why random matrix theory has anything to do with this, right? I'm talking about polynomials on the sphere. Where are the random matrices, okay? So for Kac-Rice, if you don't know what it is, my minute of publicity for Jean-Marc Azaïs and Mario Schweber book, and there are 2 very good books, this one and the book by Adler and Taylor, and of course the session we had yesterday on this. And these 2 books are really nice, and both happened essentially, were published essentially at the same time. Needless to say, I learned in Jean-Marc's book. Okay, so the Kac-Rice formula, let me remind you what it is. So you take a smooth random function on an n-dimensional compact manifold M, and I will assume this function to be Gaussian. Okay? So here's one of the Kac-Rice formulae. The expected number of critical points of index k with values in B is obtained as an integral, where this term here is this expectation of absolute value of a determinant conditioned by this, and where here this I is the index, so you indicator of the index being k. So this is the Hessian of f, and you look at its absolute value of the determinant conditioned by the fact that f is the point x is critical, and by the value. And here you integrate on the value, and here you integrate on the manifold. And this guy here is the density of the Gaussian vector f grad f. So here, because everything is Gaussian, the triplet f grad f Hessian f is Gaussian. So this conditioning here is very simple. It's a linear operation, right? You condition in the world of Gaussians, all right? So the basic thing here is to understand the gradient, the absolute value of this determinant, all right? Be careful, absolute value is really a mess. That's the hard part of the formula, okay? If you don't have the absolute value, you're computing Euler characteristics, it's simpler. All right, so in fact, there are many other variants of the Kac-Rice formula. You could compute higher moments, for instance, the second moment of this number of critical points, or the third moments. You could also, as I just mentioned, compute the earlier characteristic of level sets, as I just described before. It's essentially the same formula, but as I said, you get rid of the absolute value. All right, but this is one formula that we will use. All right, so what's the link with random matrix theory? The important message is this: the Kac-Rice formula, which, of course, a bit of history, it's in fact the Rice formula, which was done essentially around the war, World War II, in dimension 1 for signal processing. And then Kac-Rice did it essentially just after the war in the 50s for dimension 2. It has been used a lot for fixed dimension. Here we're pushing it to a diverging number of dimensions, right? So this is in fact, I see it as a powerful link between the question of random geometry, understanding the topology of a landscape, and question of random matrix theory. So why? The link with random matrix theory is simply that in this formula, you've seen that you have to understand the Hessian. But the Hessian, or the Hessian conditioned by other things. But this Hessian is, of course, now a symmetric, real symmetric, n by n random matrix. Gaussian, in fact. So this is where the random matrix is, right? You have to understand the law of this random matrix conditioned by the gradient and by f. And if you're lucky, this is a random matrix that fall in the class of random matrix problems that we understand. If you're not lucky, you have to work. Okay, so this is just what I said. How do you see what kind of matrix it is? The covariance structure is in fact a 4 tensor, right? The covariance between ij and kl, which you obtain easily by differentiating the covariance of your initial function. So you have access to it. Plus some linear algebra if you take into account the conditioning. That's a general recipe. I give you a Gaussian landscape, you have to solve a random matrix problem. All right, so this class of models, in fact, Gaussian thing with correlated entries is in fact difficult. It's not one of the classes that are natural. It has been studied recently by Laszlo Erdős and his collaborators, and we are still pushing this, but this is not completely established things. But there are important classes of examples, subclasses, where the random matrix model is tractable. And this is what I will do here. So I will study 3 classes of example. One, I already, so one which will be spherical spin glasses, so statistical mechanics, disordered media. Another one which is a hard problem, which is Tensor PCA, Tensor Principal Component Analysis. So the last 2 are problems in high dimensional statistics. And the last one is generalized linear models, or for machine learning, this would be one node network. Of course, we hope to understand more complicated models of machine learning in the future. All right, so let's start with example 1. So what is this question of statistical mechanics? You look at a random Hamiltonian defined on the sphere, and for a natural reason, the sphere is of radius square root n, you could put it on radius 1, and this Hamiltonian up to a normalization is this, where the coupling constants here are IID and Gaussian, right? So if you had only 2, and if P was 2 and this coupling constant here were 1, you would essentially looking at the Curie-Weiss model. If this coupling constant were, if P was 2, this is the famous Sherrington-Kirkpatrick model, but in the simple spherical form, right? And when P is anything, this is called the P-spin spherical model. All right, so that's what you do, of course, in statistical physics. You give this Hamiltonian, and you want to understand the Gibbs measure, which is exponential minus beta h, right, on the sphere, normalized. So how does the Gibbs measure behave as a function of beta, which is the inverse temperature, right? So this is a long story. You've heard about it in Saurav Chatterjee's talk yesterday. And so, of course, that's what we understand. The approach here is not to do what we do in statistical mechanics. In statistical mechanics, you look at the Gibbs measure and you prove all sorts of things. Essentially, you only have one tool in math, and that's integration by parts. So you prove Guirlain-Daguerre, and then you work hard and you say something about the Gibbs measure. Here, we start with just the Hamiltonian function, no entropy, right? The temperature 0 thing, and try to understand its shape first. But of course, if you look at it, this is exactly the example I gave you. We already know. I told you the results about these things. This thing is a homogeneous polynomial of degree p with random coefficients up to normalization. So no surprise, this is a complex function. Right? This is why I started with homogeneous polynomial. Who cares about homogeneous polynomial except that these are the right models? Okay, so there is a long story. I don't want to go there because that's already kind of established now. So in a long series of papers, we understand, for instance, the first question, what is the minimum of this? Right? So for physics, it would be, what is the ground state? Hard question of physics or optimization. And physics has a way to do that, which is to compute the free energy at positive temperature and then let the temperature go to 0. Right? You compute the free energy using the Parisi formula, which you've seen yesterday or allusion to yesterday in Surav's talk. If you can compute the variational problem, which is in the Parisi formula, you can compute the free energy, and then you can let the temperature go to 0. And you find a definite value. In this case, the definite value is negative 1.6 something times n. Right? So here you can do it directly by just looking at this thing and try to understand where the local minima are. In fact, what we can compute here is the complexity of critical points at fixed index below a given level, what I told you yesterday. So why is that? Because in the formula we had before, the random matrix problem here is simply the simplest random matrix there is. It's the GOE, the Gaussian orthogonal ensemble. Why? Because in fact, this model has an invariant by the orthogonal group. And this invariance tells you that the GOE must be close to, the Hessian must be close to a GOE. In fact, it's a GOE shifted. So you know a lot about random matrices like that. You know large deviation principle, which I established more than 20 years ago with Alice Guillonnet and then Amir Dembo. So you have everything you need to compute this anneal complexity. You can compute the topology of level set. You can even compute the quench complexity. So what does anneal mean? Anneal means that you're taking 1/n log of the mean number of critical points. But what you're really interested in is expectation of 1/n log of the number of critical points. Putting an expectation outside of a log is non-trivial. You have an inequality by Jensen, but it's a non-trivial fact. And that's one of the very hard defects of the Kac-Rice approach. The Kac-Rice approach does not give you the distribution of the number of critical points. It gives you all its moments. And in hard cases, and most interesting cases, this is not enough. So here, in fact, the quench complexity has been computed only at very low energy levels. At very low values, we could prove that the anneal computation, the Kac-Rice computation, not we, Eliran Subag could prove that the anneal computation was correct because there was concentration. The second moment was essentially very close to the square of the first moment. So all that is done in this series of paper with Tuka Finger, Yirji Cherny, then taken up by Subag in his PhD, and Subag and Zeytouni for the lowest local minimum. So the picture is this thing is extremely complex. All the local minima are down. You can compute where they are, you can understand how many you have, you can understand the topology of the level sets, and this gives you, of course, the next step, which is understanding what this tells you about the Gibbs measure. Once you understand so you see, it's an alternative thing. I don't compute directly the free energy. I try to use a complete understanding of the shape of the landscape to understand the Gibbs measure. And this has been done. So once you understand precisely the bottom of this energy landscape, you can get very sharp, the best possible information on the Gibbs measure at low temperature in a beautiful paper by Eliran Subag in 2017. In fact, it gives a very precise, detailed geometric picture of what is called the 1RSB phase. So let me tell you what the picture is with my hands. You have this high-dimensional sphere. You can look at the lowest possible energy points. They are essentially orthogonal, these local minima, the lowest possible. And then when you take around each of them, you have a little circle. Of course, a circle on a sphere of dimension n-1 is itself a sphere in dimension n-2. So if n is 10 to the 9, it's still a very big dimensional thing. And the Gibbs measure is essentially concentrated on these little circles. Okay? And you can explain that even more precisely. But this tells you that the overlap, that is when now you take two replica, if you have followed the class, the course, the talk by Shorav yesterday, if you take two independent replica from the Gibbs measure, two things can happen. Either they fall in the same well or in two different wells. If they're in two different wells, their inner product, their overlap will be zero. So these things are essentially orthogonal. If they fall in the same well, their overlap will be a positive thing. So the distribution of the overlap has two atoms, 0 and this radius of the circle. That's what is called 1 RSB, right? 1 RSB means the distribution of the overlap has two atoms, right? So you see that the description I'm giving you now, the geometric description, gives you much more information than just saying that the overlap has two atoms, right? This description I'm giving you here is what Shorav was describing yesterday in terms of, breaking the big space into smaller bits. Here, the smaller bits are these wells centered on the deepest minimum. Okay? And so, for instance, this description implies that there is no chaos in temperature, which means that if you take the Gibbs measure at two different temperatures, they look very much alike. Because here they are just those circles in the same wells. Anyway, and this confirmed this ultrametric structure that you heard yesterday by Shorav in a very, very precise way. In fact, you can even push this to model now enough with homogeneous polynomials, we know that there are other polynomials, so take a non-homogeneous polynomial, right? This is, in physics, it's called a mixed model, right? So you take a P and a Q, and you mix these two Hamiltonians, right? This can also be done. This was done in this paper, and then in this paper, and this very recent paper, which will appear soon with Subag and Zaytouni. So we have a lot of information, but a lot more needs to be done. So if you want good problems with Kac-Rice, this is one. In particular, for instance, it's important to understand the quench complexity, and in this case, in particular, what is called the full RSB cases, which happen there. In these cases, computing the second moment will not be enough. In the hard cases, you can prove that you can compute as many moments as you want with Kac-Rice, and you will not understand the complexity. Kac-Rice is bad for that. So you need other things. The physicists, of course, have good methods for that, replicas, replica trick, but for us, it's still a challenge to know what to do in these cases. Kac-Rice is good when the problem is simple. So if you want, so that's what I'm saying here. Kac-Rice is an annealed formula. It deals only with moments, and there are many most of the interesting hard cases, computing the moments is not enough. So if you want to jump in, please be my guest. Here is a nice problem. Take a polynomial of degree 3 and a polynomial of degree 16, random, right? Now, what we know with these results is that if your mixture is very close to 3, or close to 16, in this paper, we established that there is 1 RSB, we understand the whole structure. But if you're in the middle, there are papers by physicists a long time ago, Cavagna, I think, predicting that in the middle, you will have a 2 RSB phase, which is still doable, and a full RSB phase, a place where you can forget about Kac-Rice. So here's a nice problem. Do Kac-Rice, understand what's going on for 3 plus 16. Okay? Looks like simple, but it is not really. All right, so now let's move to statistics very quickly, because it's another source of random function in very high dimensions. So let's say you want to estimate a parameter. One natural thing to do is to minimize a risk, a loss, or maximize a likelihood, or a log likelihood, like we've just seen. So typically, of course, you would want, this is exactly what we heard you would want to minimize the population risk if you knew F0 in the preceding talk, but of course you can't do that. So here's a parameter in dimension n. This is a loss function, for instance, the negative of log likelihood. This x is the data you have, which stays in RD. So since you don't have access to this function to minimize, you of course do a sampling thing. You just take an empirical risk, where these xi's are IID, sample of the distribution. So now remember, this is the curse of this type of problem. Nobody uses the same notation. So n is the dimension of the parameter, d is the dimension of the data, and m is the size of the sample, right? You take any other paper, these things are shuffled, so you can't read. All right, so a good question now is, this function, of course, now, is typically a function, a random function. It's random because of the data, the xi. It's a random function in theta, which is in dimension n, and my n will be 10 to the 9. So it's a random function of very many parameters, a little bit like the Hamiltonian before. So the question is, can the minimization of this be a good substitute for the minimization of the true thing? Typically, or the true, or at least the best you know. Of course, in classical parametric statistics, m tends to infinity, the size of the sample. These guys are kind of fixed, so we know yes. But when the dimension is large, either the parameter or the data dimension, then the problem is much harder. And this is, of course, the case for many important problems today. So, of course, you see me coming now. This function will be complex. Not always, otherwise we could do nothing, right? But sometimes they are complex. So, oops. All right, so here it is. So this function here will, a smooth random function of any variable, very often non-convex. Optimization, this is what we'll be talking about here, might be difficult. So the first question would be to understand the complexity of the random landscape of, let's say, likelihood. The next question is to understand, once you understand the geometry, this is a geometric question, the next question is algorithmic. Choose an algorithm to go down in this landscape, whichever you want, and then understand the performance. So for instance, stochastic gradient descent, Langevin if you're a physicist, all right, or anything else. All right, so the question is, what is the role of the algorithm? What is the role of the initialization of your algorithm? Is that difficult to find the minimum? Can you find the minimum? So here is an example. This will be my second example. The third will be in the same family. So this is an example of a hard example, Tensor PCA. So here it is. You observe, let's say, an M sample of a noisy P tensor. So you have a P, your data is a P tensor, V to the P, and you have some noise. Let's say here, so these are random IID P tensors, let's say Gaussian, okay? So here you see, I'm observing a very sparse thing. I'm observing a rank 1 tensor. This is a rank 1 tensor, but it's noisy. And lambda, of course, will measure a signal-to-noise ratio. So the objective is to detect, to recover this V, which is the signal, okay? Of course, you could ask the same question, is the signal, instead of being of rank 1, where a rank 17, the formula will be more terrible. So detect means realize that there is something. Recover means finding V, okay? And here we're in a very large dimension. Okay, so assume that the noise is Gaussian. You assume no prior information on the spike V. Say, for you, it's a unit vector, uniform on the sphere. And this problem has been well studied. You have, in particular, very important work by Montanari and Richard, and then Reichmann and Zeytouni. This paper by the Paris team, Lezior, Miolan, Lelarge, Chiakala, and Zdeborova, Perivine Bandera, who was then my colleague at Courant. So there are three thresholds. There are three questions you can ask for this problem, as every problem in a very high dimension. The first question is detection. And it's usually called the IT, the information theory threshold. The question is it possible to detect the signal, right? If the total variation distance between the distribution with the signal or without a signal tends to 0 when your dimension grows, then even if you're the god of statistics, you can't separate them, right? So you cannot detect, even know that there is a signal, right? So the IT threshold is the moment when lambda is large enough where you can detect. Question 2 is recovery or estimation. That's called the statistical threshold. Then the next thing is, say you are above the IT threshold, so there's something to be done, you pick a statistics. Oops. Revisor orthographia. Okay. Thank you. So let's say you pick a statistical method, the one you like. So for instance, plain vanilla methods like maximum likelihood estimation. And so once you have a statistical method, above what threshold is the estimator of the signal better than random? Because when you're in very high dimension, is your estimate not even consistent, good, converging but just better than random? And then of course you could ask, when is it really converging to the true V? So that's called strong or full recovery. And then there's a third question, which is the computation. Now, once you've picked this statistical method, say MLE, then you pick an algorithm to find this maximum likelihood. And you just don't say simply find argmax. How do you find the maximum? So for instance, you take gradient descent, SGD, or anything you like, and for what signal-to-noise ratio do you recover the signal? Importantly, in short time scales. You don't want a time scale which is exponential to the n, because if n is 10 to the 9, then you're dead before the end of the algorithm. So you want short time scales. And this is a very different problem than the one I've been studying for years in physics. In physics, when you look at convergence to equilibrium for this type of thing, typically at low temperature, because of the roughness of the landscape, the convergence to equilibrium is extremely slow. It's exponential in n. The system ages. But you don't want to get into this regime. You want to be there for a short time. So you're studying the behavior of dynamics that tend to get trapped, but before they get trapped. Okay, so it's well known and that the detection threshold is 1, let's say with the right units. And below this threshold, the two distributions are indistinguishable, and above they are positive asymptotically. So there exists a statistical procedure to differentiate them. Okay. Question 2, let's say you take MLE, so that's what I understand, and what is the threshold? Interestingly, in this case, so the threshold must be above this one. In this case, they are the same. We proved that, but it's still a mystery. In fact, the question is, when is it possible to detect the signal? So when it is possible to detect the signal, in fact, you can recover it by the plain vanilla method, by MLE. You can recover it partly, of course, partially. And of course, this question is the question where the Kac-Rice formula is useful. Because now you have this landscape of likelihood, or log likelihood, and you want to understand whether it's complicated enough or not to where are the local minima? Are they correlated with the signal or not? So this is recent work with Andrea Montanari, Song Mei, his former student, Mihai Nika, my former student, and this will appear. This is a purely mathematical paper that uses Kac-Rice and compute the anneal complexity, and is fully rigorous. Computing the quench complexity is very hard, so this is what we did here with Valentina Ross, Giulio Biroli, and Chiara Camarota, all physicists. So in this paper, we are allowed much more power, right? That is, we prove something like what physicists say is exact, which we would say is not rigorous. But it's still true. So, so here we introduce a new method, which is called replicated Kac-Rice, using the kind of magic of replica trick for the Kac-Rice formula. Of course, needless to say, I would love this to become rigorous. If anybody wants to try them, that would be nice. Okay, so staying in this example, I want to talk to you about the gap. So in fact, the question 3 in this example now, once, let's say we have understood the shape of this landscape, the question is, what does the algorithm do? So in fact, if you take the simplest optimization algorithm, the only one I understand, which is, let's say, gradient descent, Langevin dynamic, or stochastic gradient descent, they work in short time scale only when the signal-to-noise ratio is larger than this threshold. So when P is larger than 3, let's say P is 3, this is n to the 1/2, which means that you have an enormous gap, right? If you just say maximum likelihood works for lambda equal 1, works if you're the god of optimization, right? That if you know how to find the maximum of the likelihood. But if you try to find the maximum of likelihood by just doing the natural optimization, you need an enormously larger signal-to-noise ratio, which means, in fact, many more data. This is a huge gap, and this is which means that this problem is a really hard problem. Okay, so for a long while, we had p minus 1 over 2. It took us something like a year to go from p minus 1 to p minus 2 over 2. But this is optimal in the following sense. So this gap is called the so-called computational statistical gap. And in fact, this threshold is also the threshold for many other algorithms, which are not plain vanilla, like gradient descent. So for instance, things that come from the Bayesian side or from the physics side, the TAP side, the approximate message passing, for instance, pushed very much by Florent Chakala and Lenkas de Borova, so for instance in this paper, all the natural algorithms like this block at the same place. In fact, there are other algorithms, less naive, that works better, and with this threshold, p minus 2 over 4. But so for p equal 3, it's n to the 1/4. Still, you need an enormous amount of data to be able to find something. So let me explain what happens below this data for gradient descent. Below this threshold, so let's say your signal, this is the sphere in dimension 1,000,000. This is the North Pole, which is your signal that you want to find. And you start with a point at random. If you start with a point at random, it's on the equator with respect to this North Pole. And the equator carries essentially all the mass of the sphere. These two hemispheres are tiny in terms of mass. So when you run your gradient descent algorithm, there's also something else, as we will see, is that the drift, the signal produces a gradient near the equator that vanishes. And its derivative vanishes, and its second derivative vanishes. So the signal is extremely weak in the region of maximal entropy, right? So below this thing, you just stay there, right? And in short time, you will reach this thing, but in time exponential. All right, so these less naive algorithms include semi-definite relaxation, the SOS hierarchy, sums of square hierarchy, so for instance, Benarous. Very recent work by Alex Vine from Courant, Alalawi and Moore, the Kikuchi hierarchy spectral algorithm, and the same group of physicists introduced very recently also this replicated gradient descent. All these super smart things, very different, all end up being blocked there. So there is a real gap that you can't really, of course, it could be that somebody comes up with a completely different algorithm that closes the gap. Honestly, I don't believe. All right, so let's go back to what we understand, which is the MLE. So when you want to estimate the likelihood, this is what you want to find. And when you look at what the likelihood looks like, it's like this. Well, these guys are Gaussian. They are the coefficient of the tensors. Okay? So by assuming that you can always rotate your signal, making to the North Pole, here is the function you want to minimize. So look at it. This is exactly our old friend, the homogeneous of degree p polynomial on the sphere. That's the spin glass model. Except that now you add this signal, right? So if you had only this function, this is not a Morse function, this function, let's say x1 is this axis in my sphere, this function will have a minimum, depending on if p is even or odd, will have a minimum at the South Pole and a maximum at the North Pole. And then plenty of critical points on the equator. But you add this random function here, which messes things up. And so what we can prove is that, of course, when there is no signal, this is just what I said, this function is the p-spin spherical Hamiltonian. We know it is complex. And so the question is, does this likelihood function stay complex when the signal-to-noise ratio increase? And when it's very large, right? So, and what we need to understand, if the global minimum of this, which will be the MLE estimator, is close to the signal, to the North Pole, to check partial recovery. But in fact, this function is very complex and has exponentially many local minima. So where is the global minimum? Is it near the equator? Then the algorithm will never work. Or is it close to the North Pole? Okay, so use Kac-Rice again. And now using the dictionary I mentioned, this random matrix problem brought by the Kac-Rice formula is the following. It used to be the GOE, but now the model is no longer invariant by rotation because you have the signal. So what you get here is a rank 1 perturbation of the GOE, a spiked GOE. This has been well, so the question is, when does the top eigenvalue of a spike GOE get out of the bulk of the spectrum of a GOE, which, as everybody knows, is a semicircle? This is well understood. It has a name. It's called the BBP transition. And there's a long series of work. The question was asked by Ian Johnston, and it was starting in 2005 in this paper. That's why it's called BBP. And it has been continued. There's a long list of works since then by Sandrine Péché, Mireille Capitaine, etc. So the important result we need here is, in fact, a large deviation for principle for the top eigenvalue of the BBP, which has been proven by Bill and Maida a long time ago. So the results are the complexity is always exponential. Around the equator, the function is close to the pure spherical spin glass. Look at y. Oh, it's too far, sorry. Yeah. When u1 is close to 0, that's close to the equator, this term is tiny. And so it's close to this. So you always have the complexity at the equator of a spin glass. So it's always complex, whatever the value of the SNR. When lambda is larger than 1, you have a ring of critical points which appear at a positive latitude, close to the North Pole, closer than the equator. And this one contains the absolute minimum, the MLE estimator. And the number of critical points in this ring is sub-exponential. Right? So this, what Kac-Rice tells you, and in particular then this tells you that you have partial recovery when lambda is larger than 1. And this 1 is the threshold given by the BBP transition, and it's kind of a miracle that it's the same as the IT threshold. Right? You could imagine that there are better statistical procedure than MLE. Right? MLE is for dummies, and it's for me. But for professionals, you think maybe you can do something better. And in fact, you can here. When lambda grows, the latitude of this ring grows and comes close to being the North Pole. So you have asymptotic strong recovery. In this case, the MLE converges to the signal. All right, so if you want a result, here is a result. We compute the anneal complexity, and it's given by a variational problem, which is given by these formula, which you don't want to read. But at least, there are self-contained formulae. Okay? So that I essentially already said. So now what about the gap, the algorithm? So this optimal threshold result for the gradient descent, Langevin, et cetera, obtained in this paper with Ghessari and Jagannath. So why is it? This is what I was telling you. The difficulty there is to escape the equator, what I call escaping mediocrity, right? Being as mediocre as a random person on the equator. You want to be close to the signal. The hard problem is to escape the entropy of the equator because you have a very weak signal, okay? So, and even in the simple phase of the topological transition, when you have a signal close to the, a ring close to the North Pole, you cannot escape impossible in polynomial time. So this is what I was saying. So what happens, how does these two terrible things conspire to block the algorithm? Your signal is too weak at the equator, so you just hang around the equator for too long. And the equator is a dangerous zone because you have an enormous number of wells wanting to trap you. If you stay too long, you end up in a well, and there goes your algorithm, because then you spend an exponential time in it, right? So complexity is there to catch the people who can't escape mediocrity. Okay, that's the truth in this thing. If your signal-to-noise ratio is above this threshold, then you zoom fast enough away from the equator and you don't have to deal with the complexity. Okay? Let's finish with a more complicated problem. So this problem is a priori in the class that computer scientists or mathematicians love because they are complex. We love complex problems. Of course, if you're a statistician or machine learning, you want to avoid these problems, right? Because these problems tell you there's nothing you can do except having a huge amount of data. So let's look at other problems. So I will look at the following two loss functions. So the first one is what is called the perceptron in physics. It's just 1 over m, a mean of phi, what is called an activation function. And these guys are IID vectors, and this is the inner product. X is in the sphere, so you take the overlap between random vectors and a given point, and you take this thing. Okay, here's another one, which is the planted version. You have the same object, but now you have a planted signal. I called it V in the Tensor PCA. Now it's X star, that's my signal. the North Pole if you want, square. Okay? These are very natural problems, of course, statistical problem, because they cover many, many well-studied estimation problems, depending on which activation function phi you choose. For instance, if you choose phi linear, it's a linear regression, so no big deal, right? Just to check, look at this one with phi linear. I mean, this is not difficult. If you take phi quadratic, then it's called phase retrieval. You have many other things. You could have classification, sign retrieval, all sorts of things. And generally, it's called the GLM, the generalized linear model. The important thing about generalized linear models is that they are not linear. They are not the general linear models. They are the generalized linear model. So the two guys who invented it, if you go to Wikipedia, because I asked myself, why did these guys call it the linear model? If you go to Wikipedia, you will see in a note that the authors, years later, say, oh, I think we made a mistake. So it is, I think, a mistake. It's not linear, but it's what it is. So in physics, it was introduced by Derrida and Gartner a long time ago in the 80s, and it's called the teacher-student network. In machine learning, this would be a one-node network. Look back at what that is. This one is a one-node network, right? Imagine you have one node, you have entries, then the x's are the strengths of the weight, synaptic weights joining these n things to the node, right? And the size are the entries. And then you do what you do in a machine learning thing, you just take the linear combination, which is this thing, the inner product, and then you have at the output, you have an activation function, whichever you want, the sigmoid function, ReLU function, whatever you want. Okay, so that's a trivial network, one node. Oops. Okay, so there's a huge literature, too much to be even quoted here. If you want a nice recent paper, this is by this group at École Normale, where they use, in fact, the statistical physics methods to study these models in general. Not their complexity, but. Okay, so the first question I want to ask is, what is the complexity of this random function? There are, again, functions of very high dimension, random. Are they complex or not? Right? And the second question, so this is a joint work with Giulio Biroli and Antoine Maillard, and it's submitted tomorrow. So until tomorrow, in those things, in computer science type things, the authors are supposed to be hidden and so on. So you can't put that on archive until it's there, but it will be. So question two is, how hard is, once you understand the landscape, how hard is it to find the minimum, like we've seen in Tensor PCA? So this is current work with, so you take, let's say, a gradient descent or stochastic gradient descent algorithm, and you initialize randomly. So this is current work with the same gang, Ghessari and Jagannath. And so here are the results in a nutshell. So under natural smooth assumption of the activation function, we can compute the complexity of these two functions in the high dimensional setting. When both n and m tend to infinity, remember that's the size of the parameter, that's the size of the sample, and where the ratio converging to something. So this is really a high dimensional context. But we have to assume that the data is Gaussian. I hate it, but we have to. So the C are IID standard Gaussian. So why do we have to assume that? Again, a deficiency of my friend Jean-Marc's book and the Kac-Rice formula. There are formulae. In fact, the Kac-Rice formula should not use Gaussianity, right? But because in fact it's based on, and this you can see very well in the book by Jean-Marc and Schwebor, is based on a deterministic formula, the co-area formula. It's calculus 3, as we would say in math, in the US. So it's a perfectly deterministic formula. It should be valid. The problem is that it's not that simple, and so it's proven, essentially the nice formulas are proven, the nice conditions on when it's Gaussian, or, as you can find in the book by Jean-Marc and Schwebor, in an appendix somewhere in a remark, when the function, the smooth function, is a function of a Gaussian. And this is here, look at these guys. If these ones are Gaussian, this is a function of a Gaussian thing, and the same thing here, right? So you can apply Kac-Rice. All right, so, oops. So that's just what I was saying. It's a simple extension of Kac-Rice to not Gaussian, but smooth function of a Gaussian random function. And so you can indeed apply a version of Kac-Rice formula, but then, if you remember what I said, Kac-Rice is just a dictionary, because it's a very simple formula. It's the co-area formula. And it's a dictionary sending this question of geometry to a question of random matrix, right? So before, the random matrices were variants of the GOE, because we had kind of an internal orthogonal symmetry. Here you don't have that. It cannot be the GOE. So why did I choose this example? It's because in random matrix theory, you have two classes where we understand something. One are the Wigner-type matrices, which we already use. The other are the Wishart or Pastor-Marchenko type matrices, right? And this one, of course, is chosen to fall in that class. So this is what happens. So the answer is that the random matrix are generalized Wishart matrices or Pastor-Marchenko matrices spiked as before. That is submitted to a rank 1 perturbation, or here, because we have one tensor 1 perturbation. So there are rank 1 perturbation of general Wishart or Pastor-Marchenko matrices, which are this shape. Where, what is this? D here is a diagonal matrix, and X here is a rectangular random matrix with independent entries. So for these matrices, we understand the spectrum. That's a branch of random matrix which is understood. So the spectrum is well understood when the empirical measure of the entries of the diagonal converge to something. Let's say nu. And this is linked, for those who know or who like free probability, this is linked to free probability, Voiculescu probability. It converges to the free multiplicative, the spectrum of this matrix converges to what is called the free multiplicative convolution of the asymptotic spectral measure nu and the Marchenko-Pastor distribution with a ratio alpha. If you don't know what it is, just take it for granted. So we know what the limit of this spectrum is. It's no longer a semicircle, a more complicated thing, but we know what it is under this assumption. Now you have to spike this matrix by a rank 1 perturbation because of the signal. This is also known. In fact, the BBP transition, the paper in 2005, was in this context, not in the context of the GOE, in a much simpler context, but of this type. So this can be done. But something is still missing to go on. It's the MIDA result, the LDP, the large division principle for the spiked eigenvalue. It's coming, and this will allow the understanding of the complexity of local minima. For the moment, we can only compute the total complexity. We cannot fix the index. So for both this function, we compute the anneal complexity in terms of a complicated variational principle in a space of probability measures on the line. So here it is. Let me do that for L1 first. The anneal complexity, the log of the mean number of critical points, with values in B, here I don't fix the index, as I said, is a soup of, this is the relative entropy with respect to the standard Gaussian measure, and this T1 here, so you do this soup in a space of probability measure which such that the integral with respect to phi is in B, and this T1 is a rather involved thing. Here it is, a constant, that's okay. Log of this integral is still okay. This guy is a little more painful. So it's a logarithmic potential. It's this logarithmic potential. And log of x minus a constant, which is easy to compute, against a measure mu, which depends on nu. And this measure mu is this free multiplicative convolution of the Marchenko-Pastor with the image of nu by the map phi second. Right? So not easy to compute this variational problem. Done there. But nevertheless, it's completely explicit. So you can check, first sanity check, take phi to be linear or phi to be quadratic. Clearly, let's go back to what, sorry, I should have put that later. If you take phi to be, I told you it's either regression or phase retrieval. So oh, here it is. Here's phi 1, L1. If phi is linear, this is clearly a linear thing in X. Right? A linear thing on the manifold, as I said, has two critical points. It cannot be complex. If phi is quadratic, this is now a quadratic form on the sphere. Typically, the maximum critical points it can have is 2n. So it cannot be exponentially complex, right? So we should find that, and we do find that. Maybe you don't see it in the variational problem, but we checked. So So these models are indeed not complex, and it is known that the optimization of L1, let's say in phase retrieval, for linear regression it's not hard, it's not a hard problem. You don't have the gap that we had with Tensor PCA, right? Because the thing is not complex, you don't have the gap. So the real question is, for what activation functions are these models complex? So this question now is reduced to a deep, hard variational problem, right? So they are complex when this variational problem, when this soup is positive, all right? So, of course, we have also examples, but so this paper computes also the annual complexity of L2, and it's an even worse variational problem, now which includes the latitude, like we had in Tensor PCA. Right? The first one corresponds, if you want, to the spin glass. The second one corresponds to Tensor PCA. We have a planted signal, and we had the latitude. You want to understand whether you can find a minimum close to the signal. So it's even worse. I will spare you that. We can also compute the quench complexity using this non-rigorous replicated Kac-Rice formula, which we introduced with Biroli, Ross, and Camarata. And we will soon be able to compute the complexity of critical point with a fixed index, and thus the complexity of local minima, which will then allow us to see the kind of transition we've seen in the Tensor PCA for this type of thing. Of course, for the future, what you want to do is do that now not with one node, but with many layers. And the question can be different if you're looking from a statistics point of view or from a machine learning point of view. If you're looking at a statistics question, your measurement are what they are. You can't really necessarily easily play with phi, right? Whereas if you do machine learning, if you build your network, you have a choice about the architecture. You can choose the size, the depth, but you can also choose the activation functions. So probably then there is a meta problem coming up there, which is the one I just alluded to. For what choices of architecture is the task not too complex, because you don't want a gap. Right? So the question will then be, projecting in a few years, will then be first to understand this variational structure and then to understand when it is not a problem. Right? Like here, for instance, linear and quadratic are not a problem, but that's easy. All right? To characterize hard network and easy networks. All right? And so, yeah, as I said, this gap is being studied, and thank you. Yeah, but so the only Gaussian thing, let's take the Tensor PCA case, because this one is not Gaussian. But let's take the Tensor PCA. So the only thing that you have here is a trivial statistics problem. It's just a change of the mean, right? Remember, it's just u to the, or whatever, v as I call it, to the p plus Gaussian. It's the trivialist problem you can have in this terms. Identify, the covariance is not affected by the signal. It's just changing the mean. So this is, in this respect, a very simple thing, right? So what I'm saying is that precisely the IT threshold is what you're talking about. So this is, and I didn't even give a reference because this is easy. So you know that below 1, forget it. And you can say something precise, the total variation is going to 0. Above 1, total variation is not going to 0, which means that there is an event where you can separate the two things. And it just happened that the maximum likelihood is such a statistics. This is what I prove. Okay, so from this point of view, clear. The only problem is then, the optimization problem. Because it's easy to say find the argmax in this context in high dimension. If you take lambda equals 17, it will take you the edge of the universe, right? But if you take lambda equals n to the right power, it will work. Yes, of course, I think, yes. They help me. So I'm sorry, I can't hear. Function, you want to know what about functions that are not complex? Yes, this is what I told you. Yes, you have the variational problem. If this soup is positive, it's complex. If it's not complex. So this is, and it's there. It's not simply that it's an equivalent. So the problem is that complicated. But you have a criterion, okay? Of course, I'm not saying that it's tractable, because the problem is difficult, okay?
Okay, so let's think again, Gerard Benarous.